Hello everyone, this is Christian España Schmidt and thank you for being here. This is hashtag IMPOCUS, your favorite point of care ultrasound channel, and today we're going to talk about basics of Doppler. So as usual, I would like to ask you to subscribe and to follow us, as well as like, and so we can find a larger audience. So we're going to talk about Doppler. Doppler is very common. It's a common phenomenon with every waves. Anything that behaves as a wave will have a Doppler phenomena. In this case, we have an ambulance that is coming towards us. And while the ambulance is coming towards us, the ambulance will have a higher pitch. And that is part of the Doppler phenomena. And once the ambulance is going away, it has a lower pitch. So the frequency or the pitch of the source or the ambulance did not change, but what we perceive from the ambulance changed while the ambulance was coming towards and going away. And that's something that you can do every time that somebody is like even honking at you and goes and pass through or towards you and then pass you, then the sound of the honk will decrease. So not decrease, but the frequency or the pitch of the sound will change to a lower pitch. And in this case, we're gonna use a dog. Why? Because I like dogs and I like ponds, and this dog is just paddling in a pond. The dog is not moving and is creating waves, just like sound creates waves. In this case, just like sound, these are mechanical waves that are, or mechanical disturbances that are caused by the pressure of the paddling in the water. And if the dog continues to do that, and we have the opportunity to observe this, we will see that two observers, one in the back and one in the front, will see the same frequency, which equals the pitch of the sound. And it doesn't matter because the dog is not moving. So the frequency of the observer in the front and the frequency of the observer in the back will be the same. There is no way to compare, and the frequency of the source will be the frequency of the dog. Now let's say that the frequency of the source or the dog starts moving. Now there is a phenomena that changes. These circles, by the way, are the same circles I used in the illustration prior, but I just changed something. Now the dog is moving and is compressing the circles in the front, and you can see that now the frequency in the front is higher than the frequency in the back. So now our dog moves again, and again the same circles. You can see the same phenomena. There is a compression of the waves in the front that in the back, and that is because now the dog has a velocity, and that velocity is being added to the sound, and this velocity added to the sound will change the frequency that is perceived. So now if we put an observer in the back of the dog, even if the frequency of the source did not change, this observer in the back will see a larger frequency or lower pitch, and the frequency of the observer in the front will have a higher pitch or a higher frequency. And that is because now we have a velocity. So the velocity is added to the sounds in the front. They are compressed. In the back, they are delayed. And now we have different frequencies. Once the dog passes the observer in the front will see what the observer in the back is seeing. And that can happen also with the observers. If the observers have a speed or a velocity towards the source, the frequency of the source will be perceived in a different way. So there is a math to explain this. Basically, the frequency of the observer equals the frequency of the source times the velocity of the sound plus minus the velocity of the observer divided the velocity of the sound plus minus the velocity of the source. So you can see that if the source is going towards the observer, the frequency will increase. if the source is going away of the observer, the frequency decreases. Same thing, if the observer is going away from the source, the frequency will decrease, or the perceived frequency will decrease. And if the observer is going towards the source, the perceived frequency will increase. So we use this, and our machines use this in advantage. So now we have a vessel. This vessel has, as you can see, red blood cells going from a direction to another. It doesn't matter if it's an artery, a vein, or whatever other thing that is having a motion or a circulation or a motion of the fluid that is inside. And once we put our ultrasound probe, the ultrasound probe will send pulses of sound, and then we'll wait for the echoes. In this case, as you can see, the erythrocytes can reflect the echoes back to the probe, and the echo will have a higher pitch than the frequency used. This is used by the machine to figure out the direction. In this case, we are seeing a video of color Doppler, and you can see that we have a maximum velocity of sampling, so that depends on how often the pulses are going towards the vessel. And then we have a scale that tells us that anything that appears red is going towards the probe. So this is an abdominal probe, and everything is going towards the probe, it will be red, and everything that's going away from the probe is going to be blue. Most of the circulation here is from the renal artery, and you can see some of the renal artery going away in the bottom, and that is represented as blue. So it doesn't matter if this is venous or arterial. The important part is what is the direction of the sound. Same here. This is my brachial artery, and we have a maximum velocity of sampling. It's higher, and again, red towards blue away. And now I have the probe slightly rotated or tilted against the artery, so the flow is going towards the probe, and that's why it looks red. It's not because it's an artery, but because the flow is going towards the probe. There is another way to figure out this. We can also create what we call spectral Doppler. And in a spectral Doppler, we have an XY axis where the positive is going towards the probe and the negative is going away from the probe. Usually we have the positive on top and negative in the bottom. It all depends on how the settings of the machine are. But for point of care ultrasound in medicine, this is going to be the way. So in one of the most used spectral Dopplers is pulse wave Doppler. And in pulse wave Doppler, you actually can sample a specific place. And in this case, we're specifically sampling the portal vein right between those bars. You can see that the portal vein in the coronal Doppler appear red, so it's going towards the probe. And then you can see the spectrum. And the spectrum down, you can see a bar look like spectrum. And it tells you that it's going at 20 centimeters per second. In the x-axis, you can see the time, -6 seconds, -4 seconds, -2 seconds. And then you can see the 0 seconds. And how fast this is going is 33.33 millimeters per second. And that is a normal ultrasound of a portal vein. This is how a portal vein should look. This is the velocity of the portal vein usually. Of course, we can again sample my artery, my brachial artery, and then you can see now same thing. We have positive, and then we have negative, and then we have a 0. In this case, you can see that the time is going -5 to 0 in the y-axis of the spectrum. And that is because this is the way that our machine is, the settings are placed. You can see that we are sampling in an artery. In this case, we don't have the red in the artery, but that's where we are sampling, where the bars are. And we are obtaining pulses of about 50 centimeters per second maximum in the in the um, in the spectrum. So now, what will happen if we just change the probe position? So look at this. Now we change the probe position and we have flow that is going away. As you can see, the flow is going away and the rebound of the sound or echo, it's having a different wavelength. So a lower pitch from our prior example. This is very useful because now we can figure out that the flow is going away from the probe. And here is our kidney again. You can see the kidney with red and blue, and all these areas, red, are going towards the probe and the blue are going away from the probe. You have, again, the maximum velocity of sampling, and you can see that it's 22 centimeters per second and minus 22 centimeters per second. And anything that is red is going towards the probe and blue is going away from the probe. And there are a few areas of the kidney that have blue flow during systole, which are just arteries that have a flow that is going away from the probe. Here we have an hepatic vein. Again, you can see that we have a spectrum down, and this is a pulse wave Doppler that is sampling that hepatic vein right in the line with the two bars, and we can see the spectrum that is negative. So this hepatic vein is going away from our probe and is looking negative. And this is a normal hepatic vein Doppler. Here again, we're going to see my radial artery, but now I have changed the position of the probe. And once I play this video, you're going to see that the artery looks blue. So it's not about it's an artery or a vein, it's about the flow. Here we have the spectrum from a portal vein, one of the vessels that I check the most because of volume status and patients who have cirrhosis. And we can see the flow of the vein is going towards the probe, therefore is red. And anything that is going away, there is nothing going away, because if you can see down in the spectrum, you can see the continuous flow of the portal vein. There is another vessel creeping in this one. Every crest that you see is also an hepatic artery. Again, that's the sample indicator, and we are measuring the spectrum right from there. So anything that you see in that strip of the spectrum down is what is measured in that specific sample indicator. Again, these two bars show a sample indicator right in an hepatic vein. An hepatic vein is blue because it's going away from the probe. And after -3 seconds, you can see down in the spectrum, in -4, -5, I was not able to sample the vessel. But in -3, -2, and -1, I can get a very good sample, probably because the patient was breathing and the indicator got off for a few. We have now some ultrasounds that can change that indicator with the respiratory pattern of the patient, but this is not one of them. And we can see how we can see the normal curves of the hepatic vein flow. Lastly, we can see here a nodule, a subcutaneous nodule that I found in a patient. This nodule was scanned and resulted to have all these orange spots. So this orange spot is something that we call power Doppler. So power Doppler, it's ideal to see low flow, and this doesn't give you a direction. We know that there is flow. As you can see, there is a bar, an orange bar to the left, and that bar just tells you that there is a Doppler, that's the color of the Doppler, or the color that the Doppler will appear in the screen. So we have a 2D image that is showing us flow all over the place. At the beginning, I was hoping that this will be a lipoma or something like that, but after seeing this and with the history of the patient, we sent this nodule for biopsy being positive for a carcinoma of the abdomen, and this gives us a very quick diagnosis for this patient. Well, so this is my take on Doppler. Thank you for staying to the end, and hopefully we will have new videos. Give us a like, give us a comment, tell us what would you like to see, and thank you very much.